Let's talk about the reaction of haloalkanes with metals. Now, when we talk about the reaction of haloalkane with metal, then in that case, let's consider that we have an alkyl halide Rx and we react it with a metal. Now, let's say that metal happens to be sodium. Now, when alkyl halide reacts with sodium, sodium being a reducing agent will give an electron to halogen. When halogen gets the electron from sodium, then in that case it reverts the electron of carbon to carbon and takes the electron from carbon. What we get an alkyl radical along with NaX. Now this sodium has a capacity to react with alkyl radical as well. Another sodium atom is going to react with this alkyl radical and shift its electron towards the alkyl group. So we are going to get R minus Na plus. So we are going to get a species, sodium alkylide, which is going to be a kind of anionic compound. Now, this compound being ionic, the carbon has a negative charge. It's a very strong base. Please remember here, sodium ion is not the reactive species. It is the carbon anion, carboanion, which is the reactive species. So any reaction that we can consider, then we can ask about is the reaction of the alkyl group. If we have any hydrogen which is present in the reaction mixture, then R minus being a very strong base is going to accept the H plus from any H plus donor. This H plus donors obvious could be water, it could be alcohol, it could be amine, it could be any other acid as well. So this R is going to react with H plus and it is going to give us RH, that is alkane. Now, this could be a reduction reaction in which alkyl halide is getting converted into alkane. For this particular reaction, if we have to convert the alkyl halide into alkane using metal and H+, then the reaction can be generally written as Rx reacting with metal and H plus gives us RH along with metal with the halogen. Now, the metal and H plus, the source of H plus, are according to what we have the metal. If we have a reactive metal, then in that case we have a reluctant source of H plus. And as the reactivity of metal decreases, the H plus activity increases. Like if we are going to use sodium for this particular reaction, sodium is used in presence of C2H5OH. So we use sodium alcohol as the reducing agent. If we are to use magnesium, now magnesium has a lower reactivity as compared to sodium. So here the H plus source is better than C2H5, we use water. If we are to use instead of magnesium, if we use zinc, then in that case H plus source turns out to be acetic acid. If we have to use even a weaker metal, something like iron or tin, if we have to use iron or tin, then in that case, H plus source turns out to be HCl. So as you can very well see, as the reactivity of the metal decreases, the source of H plus becomes more active, or rather it becomes more acidic. Now, once we have talked about this particular reaction, there could be a reaction in which we do not have the source of H plus. Like we can have the reaction of the alkyl halide with sodium in presence of dry ether. So we do not have any source of H plus. When we talk about dry ether is ether which does not have water, but dry ether basically means CH3, CH2, OCH2, CH3. This is what we have as dry ether, diethyl ether, which could be written as E2O, or it could be written as C2H5 whole twice O. Another ether which is used when we have the aromatic groups is this compound. Now, this compound is what we call as tetrahydrofuran, THF, tetrahydrofuran. This also is used as an ether or a dry ether in this case. Now, the reaction, whether it takes place in presence of H plus donor or it takes place in presence of dry ether, the reaction initiates in the same manner. That is, we do get the R radical and we get NaX. Now this R radical reacts with another atom of sodium to form R minus, Na plus. Now in this particular reaction, we do not have any source of H plus. So when we have R minus, it's an extremely reactive species. So this is going to look for a positive charge in this particular reaction. Now the positive charge is not sodium. The positive charge that we can get in this particular reaction is another molecule of alkyl halide. Now, due to the presence of halogen with the carbon, this particular bond is polar and carbon has a partial positive charge. This negative charge can attack on the positive charge of carbon. The bond cleaves and we get RR along with NaX. If we add the entire reaction, we get 2Rx plus 2Na, giving us RR plus twice of NaX. Now, this particular reaction is called the Wurtz reaction. We will call it Wurtz coupling reaction or the Wurtz reaction. Now, let's consider some example of Wurtz reaction. Let us say we have CH3Br reacting with sodium. We can easily write this particular reaction as CH3Br plus 2 sodium, or I'll take it as CH3Br plus sodium. Let's talk about the mechanism of this particular reaction. The mechanism would be CH3Br initially is going to react with sodium, and then it is going to give us CH3 radical along with NaBr. This CH3 radical is going to react further with sodium to form CH3Na minus, CH3 minus Na plus. This CH3 minus Na plus is going to react with another molecule of CH3Br. This electron pair is going to attack on the carbon and this bond would be cleaved off, and we are going to get CH3 CH3 plus NaBr. The overall reaction here can be written as twice of CH3Br reacts with twice of sodium to give CH3 CH3 plus twice of NaBr. In the same manner, let's have the reaction with CH3 CH2Br with Na. Considering this particular reaction, again the mechanism would be the same. CH3 CH2Br is going to react with Na. Here it is going to give us CH3 CH2 radical along with NaBr. This CH3 CH2 radical will react another atom of sodium to give us CH3 CH2 minus Na plus. This CH3 CH2 minus Na plus is going to react with another molecule of CH3 CH2Br. The attack of the electron pair here will take place on the carbon, the CH2 carbon, that is carbon attached to bromine, and it's going to give us CH3 CH2 CH2 CH3. Please remember the bond, the carbon has a valency of 4. Don't make the valency of carbon to be 5 or 3. It has to be 4 and plus NaBr. So overall reaction, if we write, this is going to be twice of CH3 CH2 Br reacts with twice of Na, gives us CH3 CH2 CH2 CH3 plus twice of NaBr. So that would be the reaction of bromoethane with sodium in presence of dry ether. Now let's consider a peculiar case where we have CH3Br and CH3CH2Br and we react it with sodium. Now what is the product that we can obtain? Now here, when we talk about this particular reaction, we are going to get CH3Br reacts with sodium to form CH3 radical plus NaBr. Now this CH3 radical reacts with sodium to give CH3 minus Na plus. Now this CH3 minus Na plus now can react with any of the two species present in the reaction mixture. It can react with CH3Br, which is present in the reaction mixture, and it's going to give us CH3CH3. And it can also react with CH3CH2Br, which again is present in the reaction mixture to give us CH3CH2CH3. In the same manner, if we have CH3CH2Br, the CH3CH2Br can react with sodium, and it will react with sodium to form CH3CH2 radical plus NaBr. The CH3CH2 radical can react with, and it will react with sodium to form CH3CH2 minus Na plus. This would give us CH3CH2 minus Na plus. It is going to react. Now, this also has a capacity to react with two species which are present in the reaction mixture. It can react with CH3Br. If it reacts with CH3Br, it is going to give us CH3CH2CH3, that is propane. And it also has a capacity to react with CH3CH2Br. If it reacts with CH3CH2Br, then in that case, the product we obtain is CH3CH2, CH2CH3, that is butane. So the reaction of CH3Br and CH3CH2Br in presence of sodium and dry ether will give us a mixture of three alkanes, that is CH3CH3 would be formed, along with CH3CH2CH3 will be formed, along with CH3CH2CH2CH3 will be formed. So it is not that the reaction is not going to take place if we have different alkyl halides in the reaction mixture. It is that we are going to end up with a mixture of alkanes rather than getting a pure compound. Now, this particular problem leads us to believe that Wurtz reaction has certain limitation. There are three limitations of the Wurtz reaction. The first limitation is that Wurtz reaction cannot be used to prepare methane. Factually speaking, why would we like to prepare methane using Wurtz reaction? But still, that is a slight limitation that Wurtz reaction cannot be used to prepare methane. The second limitation is that Wurtz reaction cannot be used, or it is not used to prepare any haloalkane which any alkane which requires more than one haloalkane to be present. Something like odd carbon alkane or unsymmetric alkane, which are not prepared using Wurtz reaction. It is not that it cannot be prepared, it is that it is not prepared because whenever two or more haloalkanes are used in the Wurtz reaction at the same time, they would lead to the formation of a mixture of alkanes which have very near melting and boiling points and so are extremely difficult to separate. That is why Wurtz reaction is not used in those cases. Wurtz reaction is mainly used to prepare long carbon chain alkanes which are even carbon and symmetric. So that is what we have as the Wurtz reaction. We do have another reaction, and that reaction is termed as the Core-House reaction. Now in Core-House reaction, we again have an alkyl halide. We use this alkyl halide and treat it with lithium. When alkyl halide is treated with lithium, the reaction is again the same way. Here again we have the dry ether. We treat it with lithium. When we treat it with lithium, we end up with R radical plus LiX. Again, this R radical is treated with lithium to give RLi plus Li. RLi is going to be formed. Here it's going to be minus, here it's going to be plus. Now this RLi can further be reacted with CuX, cuprous halide. When it reacts with cuprous halide, twice of RLi reacts with uh, twice of RLi react with twice of CuX. No, not twice. CuX to form R2CuLi plus LiX. Now, this is dialkyl lithium copper or dialkyl lithium cuprate. This is a complex species. It's not a simple species. It's actually R4Cu2Li2, but this thing works for us. Now, this R2CuLi is more stable as compared to RNA. RNA is extremely ionic. Here we have lithium and copper, which has a higher electronegativity as compared to sodium, and therefore this particular species is a little bit more stable as compared to RNA. Hence, this particular species can be formed, and now we can add another alkyl halide to it. R-X. When we add another alkyl halide to it, R-X, then we end up with R-R dash plus CuX plus LiX. So we are going to get alkane, and here unsymmetric alkane can also be formed. Any alkane can be formed. But this particular reaction also has a restriction. This R could be CH3. This R could be 1 degree. This R could be 2 degree. This R could even be 3 degree. This R could also be phenyl. But when we talk about R dash, this R dash could be CH3 or it could be 1 degree. 3 degree, the elimination is going to take place. 2 degree elimination is going to take place, and phenyl is not going to react in this particular reaction. So here we have a restriction that R dash has to be either methyl or 1 degree. Other alkyl groups won't work in the Corehouse reaction. This Corehouse reaction can actually be used to prepare unsymmetric alkanes. Now, this Corehouse reaction as such is not there in NCRT, so it should not be in CBSE as well as in the entrance examination, but still we have done it. So that's what we have talked about, the Corehouse reaction. Now we get along with an extremely important reaction of alkyl halide, and we get along with the Grignard's reaction and the Grignard's reagent. In the Grignard's reagent, we have an alkyl halide, and we react it with magnesium in presence of dry ether. Now, magnesium has two electrons in the outermost shell. So when magnesium reacts with Rx, it is going to form R radical and it's going to form Mgx. Now, magnesium has another electron with it. So this is going to react and it's going to produce RMgX. Now, RMgX, alkyl magnesium halide, is what we know as the Grignard's reagent. This is what we call as the Grignard's reagent. Now, when we talk about this Grignard's reagent, here the carbon and magnesium bond is going to be a polar bond in which carbon is more electronegative as compared to magnesium. Now, carbon is supposed to have a delta negative charge, while magnesium, Mgx, is supposed to have a delta positive charge. This delta positive charge and delta negative charge, and when we talk about the electronegativity difference between carbon and magnesium, we find that this particular bond does have some ionic character. In fact, it is 37% ionic. Now, 37% ionic would mean that the bond is actually covalent. Yes, the Grignard's reagent is not an ionic compound, it is a covalent compound with having 37% ionic character. But when we talk about the organic compounds, even 37% ionic character is a significant amount which can allow us to consider the Grignard reagent as ionic. So most often, whenever we write Grignard reagent, we write Grignard reagent as R minus with Mgx plus. Considering R minus, R minus is the reactive species in this particular reaction. R minus is a very strong base, and very obviously it is a very strong nucleophile as well. Grignard reagent is not going to react with any species which it itself is electron rich, but it is capable of reacting with any other species. Grignard reagent will react with any species containing acidic hydrogen to give an alkane corresponding to the alkyl group of the Grignard reagent. So we can say RMgX, R minus MgX plus, reacting with a species containing acidic hydrogen to give RH, the alkane. So here it is going to be reduction reaction, simple reduction reaction. Now we need to understand what is the meaning of the word acidic hydrogen. Considering the meaning of acidic hydrogen, the hydrogen attached to a halogen, oxygen, nitrogen, sulfur, or triple bonded carbon is considered acidic hydrogen. So any species containing acidic hydrogen, if it reacts with Grignard's reagent, it's going to give us alkane. Now let's consider, and in any other case where the acidic hydrogen is not there, then the Grignard reagent is going to attack on the electrophilic center, that is a center which is having a electron deficiency where the nucleophile will be able to attack. So now let's consider how the Grignard reagent will react with various species. We have RMgX reacting with a species, an inorganic species, let's say water. When RMgX reacts with water, as you can very well see, water contains an acidic hydrogen. In fact, it has two acidic hydrogen. So RMgX is going to convert into RH along with MgOHX. So here alkane would be formed because water contains acidic hydrogen. Now let us consider the reaction of Grignard reagent with carbon dioxide, CO2. Now, how Grignard reagent will behave with carbon dioxide? Here we have negative charge, and if we consider carbon dioxide, then this oxygen is going to have the delta negative charge. The carbon has the delta positive charge, and again, oxygen has a delta negative charge. So the carbon becomes electrophilic center in carbon dioxide. The electron pair of carbon attacks or electron pair of alkyl group of the Grignard reagent, the carbon on the Grignard reagent will attack the carbon with the positive charge, which would lead to the cleaving of the bond towards oxygen. And of course, the negative charge of oxygen is going to react with the magnesium. This would form R. Here we have C, double bond O, and this oxygen with the negative charge, and we have MgX positive here. Now further, if we add any group containing acidic hydrogen, most often we are going to talk about HX, then in that case it will give us RCOOH along with MgX2. So the reaction of Grignard reagent with carbon dioxide leads to the formation of a carboxylic acid having one carbon more than the alkyl group of the Grignard's reagent. A reaction in which the organic product contains one carbon more than the organic reactant is termed as a step up or upgradation reaction. So this is a step up or the upgradation reaction getting a carboxylic acid from the Grignard's reagent. For example, if we have a Grignard reagent as CH3CH2 MgBr, which is produced by reacting ethyl bromide with magnesium in presence of dry ether, and we react it with carbon dioxide, it is going to give us CH3CH2 C double bond OO minus MgBr plus, which on further reacting with an acid, something like HBr, we are going to get CH3, CH2, COOH along with MgBr2. So as you can very well see that this Grignard reagent is going to give us a carboxylic acid. We started with ethyl magnesium bromide and we ended with propanoic acid. So one carbon has increased in it. In the same manner, we can even have phenyl magnesium bromide and we can react it with carbon dioxide followed by H plus. This is going to give us a benzoic acid. I hope you can make the reaction and the mechanism. So this is the reaction of Grignard reagent with carbon dioxide. Now let us talk about the reaction of a Grignard reagent RMGX with organic compounds such as we start with CH4. Now if we react Grignard reagent with methane, you can understand that methane does not have any electron rich position or electron deficient position. Neither it has any acidic hydrogen. The carbon is attached to sp3 hybridized carbon, which doesn't make it acidic. So Grignard reagent does not have any space, any place to attack on methane. So here we do not get any reaction. Now let's react the Grignard reagent with ethene, that is alkene. In case of alkene, we find that the Grignard reagent will not be able to attack on an alkene because alkene has an electron cloud above and below the plane of the molecule. So an electron-rich species will not be able to attack on the alkene. So with alkene also, we do not get any reaction of the Grignard's reagent. When we talk about the reaction of the Grignard reagent with alkyne, and we talk about the non-terminal alkyne, that is, the alkyne which does not contain any hydrogen attached to the triple bonded carbon. This is what we call as non-terminal alkyne. This non-terminal alkyne will again give no reaction with the Grignard's reagent. But if we have a terminal alkyne, like we have C triple bond C H, then this terminal alkyne would be containing an acidic hydrogen. This acidic hydrogen, as usual, is going to behave the way an acid behaves, and we are going to get an alkane along with C triple bond C minus MgX plus magnesium alkynide along with the alkane. That was the reaction of the Grignard reagent with hydrocarbons. Now we talk about the reaction of the Grignard reagent with maybe another alkyl halide. So if Grignard reagent is to react with R-X, now here R minus is a strong nucleophile which has a capacity to react with R and give us R dash along with MgX2. For example, we have CH3, MgBr, and we react it with CH3CH2Br. So if we are going to react it, we are going to get CH3, CH2, CH3 along with MgBr2. The reaction is similar to Wurtz coupling reaction or Core-House reaction. This again is going to give us alkane. So this is the reaction of Grignard reagent with haloalkane. Talking about the reaction of Grignard reagent with alcohols, we have RMgX and we reacted with R-OH. Please remember, this contains an acidic hydrogen. So if this contains an acidic hydrogen, we are going to end up with RH along with MgOR-X. So again, we are going to end up with alkane. If we have RMgX and we react it with an ether, that is R dash O R double dash. Now, ether does not react with the nucleophile. So here again, it is not going to be any reaction. And the example we have already seen, the diethyl ether or the furan, they do not react with the Grignard's reagent. In fact, they are used as solvent in Grignard's reaction. The Grignard reagent, now let's react the Grignard reagent with carbonyl compounds, C double bond O. When we talk about the reaction of the Grignard reagent with carbonyl compound, this is going to be R minus Mgx, here it is going to be plus. This reacts with the carbonyl group. In case of carbonyl group, oxygen has a delta negative charge while carbon has a delta positive charge. So this carbon becomes electrophilic center where a nucleophile has a capacity to attack. So as obvious, this R is going to attack on the carbon. The carbon valency is 4 and 4 bonds are already formed. So if R minus has to attack on carbon, the bond should be cleaved. So it gets cleaved towards oxygen. Oxygen gets a negative charge and the electron pair of oxygen attacks on magnesium. The intermediate species that we get in this reaction is going to be R. Here we have carbon. Here we have oxygen with a negative charge and Mgx plus. The reaction is followed by acidification. We add an acid. This H is going to replace Mgx and we are going to get RCOH along with Mgx2. So this is the product that we are going to get. In fact, we are going to get an alcohol when the Grignard reagent reacts with any of the carbonyl groups, whether it be aldehyde or a ketone. Let's have certain examples of different aldehydes and different ketones. We have CH3, CH2, MgBr, and we react it with HCH double bond O. That is methanol, that is formaldehyde. So when it reacts with formaldehyde, as is expected, it's going to attack on carbon. The bond would be cleaved. Oxygen is going to attack with magnesium bromide. And we are going to get CH3, CH2, CHHO minus MgBr positive. So that's what we get in this particular reaction. This on addition of H plus would give us CH3CH2 CH2OH. As you can very well see that the product that we have obtained contains one carbon more than the organic reactant, that is the Grignard reagent. So this again is translated as the step up reaction or upgradation reaction. So the reaction of Grignard reagent with formaldehyde followed by acidification gives us a primary alcohol having one carbon more than the alkyl group of the Grignard's reagent. So this is a step up reaction. Now we can react with the Grignard reagent with another aldehyde. Let's say we reacted with acetaldehyde, CH3C double bond OH. If you do this particular reaction, you can very well get that you are going to get CH3, CH2, CH, OH, CH3. That is a 2-degree alcohol. So the reaction of Grignard reagent with an aldehyde other than formaldehyde gives a secondary alcohol. If we are supposed to react it with a ketone, which could be any ketone for that matter, followed by acidification, we can have acetone here. Here again, it would attack over here, the bond would cleave, and followed by acidification, we are going to get CH3, CH2, COH, CH3, CH3, which is a 3-degree alcohol. So the reaction of the Grignard reagent with a ketone gives us, followed by acidification, gives us 3-degree alcohol. Having reacted with ketone, now let's talk about the reaction of the Grignard reagent RMgX with any carboxylic acid R-COOH. Carboxylic acid contains acidic hydrogen, so there is no problem with that. We are going to get RH along with R-COOMgX. Magnesium, the carboxylate group is going to be formed. Again, alkane is formed. Let's talk about the reaction of Grignard reagent with acid derivatives. We have RMgX and we react it with, let us say, anhydride. R-C double bond O, O, C double bond O, R dash. Here, the alkyl group is going to attack on the the electrophilic center. The electrophilic center again happens to be the carbon with the double bond. The bond cleaves and this oxygen will attack on magnesium. So here we get the compound as R C double bond O R dash along with R dash COO MgX. Now here we have got a ketone in this particular reaction mixture. This ketone can further react with the Grignard's reagent. If the ketone reacts with Grignard reagent and then we get R, C, O minus MgX plus R and R dash, which on acidification would give us R, C, OH, R dash, R. So this is a 3-degree alcohol. A 3-degree alcohol is formed in this particular reaction. And this is the reaction with the anhydride. Now let's talk about the reaction with the ester. So we have RMgX reacting with R dash COO double dash. If we talk about the structure of the ester, it is going to be C double bond OOR double dash. This R minus is going to attack again on the electron deficient position, the electrophilic center, and that's again going to be C double bond O. The bond would cleave, and we are going to get again, as we saw in anhydride, we are going to get R C double bond O R dash and R double dash O minus MgX plus. Again, a ketone is formed. This ketone further can react with RMgX to give a 3-degree alcohol when we acidify it. So we are going to get COH R R dash. So we are going to get a 3-degree alcohol when the Grignard reagent reacts with an ester. Same is going to be the reaction with acid chloride as well. Again, we are going to get a 3-degree alcohol. So we are going to get RMgX reacting with R dash COCl. It is going to first of all form R C double bond O R dash along with MgClX, which is going to react with another molecule of RMgX to give us R C OH R dash and R. That is what we have as the reaction with acid chloride. If we talk about amide, then in that case, the primary amide, the secondary amide, they contain acidic hydrogen and therefore they are going to provide alkane. Now we consider the reaction of the Grignard reagent with cyanide. We have RMgX and we react it with R dash C triple bond N. In this case, nitrogen is going to have a delta negative charge while carbon is going to have the delta positive charge. So the alkyl group of the Grignard's reagent will attack on the carbon. The bond would cleave. Nitrogen electron cloud is going to attack on magnesium. Now we get R C R dash double bond N. Here we have the negative charge MgX positive. Now this reaction stops here. If we want the reaction to move further, let's add a H plus here. If we add H plus here, we are going to get R C R dash double bond N H. This particular compound is called imine. If imine is further hydrolyzed, that is H3O plus is added to it, we get R C double bond O R dash. That's a ketone. Now you might ask me a question, will the reaction stop at ketone or will it get further? Like in all the cases we found that ketone was formed in acid derivative and we reacted it further. But in this case, the reaction does not take place any further. The reason to that is an extremely simple one, that is to convert or to get the imine, we had added H plus. This H plus is going to consume any Grignard reagent, extra Grignard reagent which is present in the reaction mixture. So there is no Grignard reagent left to react with the ketone formed as a final product. So reaction stops here as we don't have any Grignard reagent to react further with the ketone. This is what we have as the reaction of the Grignard's reagent.